What if I told you that one of the biggest climate solutions is not in the sky, not in space, and not in a futuristic city, but deep underground, inside rocks that formed millions of years ago? Today, we are going underground to explore a powerful question. Can artificial intelligence help us predict where CO2 will go, how much oil can be recovered, and how safely carbon can be stored in a real carbonate reservoir? My name is Votan Hung, and in this video, I will show you how machine learning can transform traditional reservoir simulation into a faster, smarter, and more visual tool for carbon capture, enhanced oil recovery, and long-term geological storage. Stay until the end, because the final results show something very interesting. Deep learning can produce high-fidelity CO2 saturation maps that are even more accurate than classical machine learning. Before we go into the model, let us first understand why this problem matters. Here is the journey for today's video. First, I will explain why traditional energy systems need to change and why CO2 storage is becoming so important. Second, we will look at the SACROC field, one of the most important long-term CO₂-EOR sites in the United States. Third, I will show how we build a machine learning workflow using reservoir simulation data. Then, we compare random forest, gradient boosting, XGBoost, and finally a 3D convolutional neural network. And the key question throughout this video is very simple. Can AI help us see underground processes faster than conventional simulation? Let us start with the global energy problem. Our world is becoming more digital every day. Artificial intelligence, cloud computing, data centers, electric vehicles, and smart cities all require more energy. At the same time, the world is facing climate change, rising CO2 emissions, and pressure to reduce dependence on fossil fuels. So we are facing a difficult challenge. We need more energy, but we also need cleaner energy. This is why the energy transition is not only about replacing one energy source with another. It is about transforming the entire energy system. And in this transition, carbon capture and storage can play a very important role, especially for industries that are difficult to decarbonize, such as cement, steel, chemicals, and power generation. The big question is, if we capture CO2, where can we put it safely for hundreds or even thousands of years? That brings us to CCUS. CUS stands for carbon capture, utilization, and storage. The idea sounds simple, but the engineering is extremely complex. First, CO2 is captured from industrial facilities or directly from the air. Then it is compressed and transported by pipeline or ship. Some CO2 can be used to produce chemicals, fuels, cement, or other products. But a large fraction must be stored deep underground in geological formations. For future climate targets, the world may need to store billions of tons of CO2 every year. That is not a small operation. That is a planetary-scale engineering challenge. But underground storage is not like putting CO2 into a box. The subsurface is complex, uncertain, heterogeneous, and dynamic. And this is the key message. In geological storage, uncertainty is everywhere, in the rocks, in the faults, in the pressure, in the flow paths, and in the long-term behavior of CO2. So the real challenge is not only storing CO2. The real challenge is predicting where it will go. When we inject fluids underground, we must also think about geomechanics. When CO2 is injected underground, it changes pressure in the reservoir. That pressure change can affect stress in the surrounding rocks. Deep underground, rocks can store enormous mechanical energy. If pressure and stress conditions change too much, faults may become unstable. In some cases, this can lead to induced seismicity. This is why my research also focuses on geomechanics and safety. In our lab, we developed an in-house simulator using Fortran and Python to study how CO2 injection changes strain and stress in deep rocks. The goal is to evaluate whether injection operations could increase earthquake risk. This is important because safe CCS is not only about storing large volumes of CO2. It is about storing CO2 without damaging caprock, reactivating faults, or creating unacceptable risk for society. Think of the underground as a giant mechanical system. CO2 injection is not just fluid flow, it is also a stress disturbance. But my research does not stay at one scale. It connects small-scale physics to large-scale impact. This slide shows the main vision of my research, from micro-scale discovery to large-scale impact. At the micro-scale, we study how CO2 moves through tiny pores inside rocks. These pore-scale processes control trapping, displacement, and residual saturation. At the reservoir scale, we need to predict how CO2 spreads over hundreds of meters or even kilometers. And at the field scale, we need to support real decisions: where to inject, how much to inject, how to monitor, and how to reduce risk. Artificial intelligence helps us connect these scales. It can learn from images, simulations, monitoring data, and geological properties. Then it can produce fast predictions that would normally require expensive numerical simulation. In other words, AI becomes a bridge between invisible pore-scale physics and field-scale climate action. Now let us move to the real field case, SACROC. For this study, we selected the SACROC field, the Scurry Area Canyon Reef Operators Committee field. This is a very important site because it is one of the oldest continuously operated CO2 enhanced oil recovery fields in the United States, with CO2 injection dating back to 1972. That means SACROC gives us something extremely valuable: a long operational history. For researchers, long-term field data is like gold. It helps us understand how CO2 behaves in the presence of oil, brine, complex wells, and real geological heterogeneity. SACROC is not just a storage site. It is a living laboratory for CO₂-EOR, carbon storage, and stacked storage potential. If we want to train AI for real underground carbon storage, we need fields like this, fields with history, complexity, and real engineering challenges. But SACROC is not a simple reservoir. Its geology is complex. This slide shows key geological features in SACROC. We can see vuggy porosity and calcite crystal growth. These features are important because they tell us that fluids have moved through the rock over geological time. Vuggy porosity means the rock contains irregular cavities or voids. These voids can store fluids and also create complex flow pathways. Calcite growth and fractures suggest that the reservoir has experienced fluid migration and mineral reactions. For CO2 storage, this matters because porosity, fractures, and mineral features strongly affect how CO2 moves, where it becomes trapped, and how much storage capacity is available. Simple explanation: if the reservoir were a sponge, SACROC would not be a uniform sponge. It would be a sponge with holes, cracks, and uneven pathways. To understand the reservoir more completely, we also need to look at stratigraphy. The SACROC reservoir is mainly associated with the Canyon and Cisco formations, which are Pennsylvanian in age. The reservoir is part of a carbonate reef complex, formed when the basin was located near the equator. Over time, carbonate sediments accumulated, and later geological processes created the reservoir architecture we study today. The main reservoir rocks are limestones, with smaller amounts of anhydrite, sand, chert, and shale. A very important part of the system is the overlying Wolfcamp shale. This shale acts as a low permeability seal above the reservoir formations. For CO2 storage, the seal is critical. It helps keep injected CO2 underground and reduces the risk of upward migration. In carbon storage, the reservoir stores the CO2, but the seal protects the storage. Now that we understand the field, what are the key research questions? The SACROC pilot study raises several important questions. First, how effective is CO2 storage when CO2 is injected for enhanced oil recovery? Second, what are the risks associated with long-term injection and storage? Third, how can we design better monitoring, verification, and accounting strategies? Most CO2 storage research has focused on deep saline aquifers, but CO₂-EOR reservoirs are different because hydrocarbons are present. The system includes oil, brine, gas, wells, legacy infrastructure, and a long operational history. This makes prediction more difficult, but also more important. So our research question becomes, can machine learning learn from reservoir simulation data and rapidly predict oil saturation and CO2 saturation maps in this complex field? This is where geology meets AI, and where underground uncertainty becomes a data science problem. Before building our machine learning workflow, we first consider previous simulation insights. Previous studies investigated CO2 trapping mechanisms in the SACROC reservoir over long time periods. This slide compares different simulation cases, such as brine-only and brine plus oil systems. The key idea is that CO2 does not stay underground in just one form. It can be structurally trapped, residually trapped, dissolved into fluids, or eventually converted through mineral-related processes. In CO₂-EOR systems, the presence of oil changes the trapping behavior. This makes the problem more complex than a simple saline aquifer case. Long-term simulation is useful, but it is computationally expensive. If we want to test many scenarios, many injection strategies, and many reservoir properties, simulation alone can become too slow. That is exactly where machine learning becomes exciting. Not to replace physics, but to accelerate physics-based insight. Now let us define the objectives of this study. The objective of this study is to integrate machine learning with reservoir simulation to accelerate predictions of CO₂-EOR and storage performance. More specifically, we want to predict oil saturation and CO2 saturation distributions using key geological and spatial parameters. Why saturation maps? Because saturation maps tell us where fluids are located. They show where CO2 is spreading, where oil remains, and how the reservoir responds over time. If we can generate accurate saturation maps quickly, we can support injection planning, reservoir management, and monitoring strategies. So the goal is not only prediction accuracy. The goal is decision support. A good AI model should not only give numbers. It should help engineers see the reservoir faster. Now we move from motivation to methodology. Now we enter the methodology section. This is where we turn a complex reservoir simulation model into a machine learning dataset. The important point is that machine learning does not start from magic. It starts from carefully prepared data. We need input features, target variables, model selection, training, testing, and evaluation. Let us begin with the reservoir simulation model. This slide shows the 3D reservoir simulation model used in this study. The model contains 13,600 grid blocks, arranged as 34 by 16 by 25. It includes 67 wells, including water injection wells, gas injection wells, and production wells. The simulation covers a long period, from 1972 to 2072, with a reservoir temperature of approximately 56.78 degrees Celsius. Here, we can see examples of oil saturation and gas saturation maps at different layers. But here is the challenge. Each simulation scenario takes a long time. If one scenario takes hours, then running hundreds or thousands of cases for optimization can take weeks or even months. This is the bottleneck. Physics-based simulation is accurate, but it is slow. Machine learning is fast, but it needs to learn from physics. So how do we convert this simulation into a machine learning workflow? This slide shows the core workflow. From the reservoir simulation model, we extract key input features, spatial coordinates X, Y, and Z, porosity, and permeability in the I, J, and K directions. These input features describe where each grid block is located and what its rock properties are. The target outputs are oil saturation and CO2 saturation over different injection periods. So each grid block becomes a data point. In this case, we generate 13,600 data points from the reservoir model. Then we train machine learning models to learn the relationship between rock properties, location, time, and saturation. Finally, we evaluate model performance using RMSE, ME, and our superscript 2. In simple words, we ask the model, given this location and rock property, can you predict how much oil or CO2 is there? Next, why did we choose random forest, gradient boosting, and XGBoost? We selected 3 classical machine learning models: random forest, gradient boosting, and XGBoost. Random forest is powerful because it combines many decision trees. This helps reduce overfitting and makes the model robust. Gradient boosting builds trees sequentially, where each new tree tries to correct the errors of the previous one. This helps the model capture more subtle patterns. XGBoost is an optimized boosting method with regularization and strong performance in many tabular data problems. These models are useful because reservoir data often contains nonlinear relationships. For example, saturation may depend on depth, porosity, permeability, and time in complex ways. We use tenfold cross-validation and hyperparameter tuning to make the comparison fair. Now comes the exciting part. Which model actually wins when we test it on CO₂ saturation maps? Let us reveal the results. Now we move to the results and discussion. This is where the story becomes visual. Instead of only reporting numbers, we look at maps, error maps, and model comparisons. Because for subsurface engineering, it is not enough for a model to have good statistics. It must also reproduce the spatial pattern correctly. Let us start with CO₂ saturation prediction. This slide compares the performance of random forest, XGBoost, and gradient boosting for CO₂ saturation prediction. The scatter plots compare true gas saturation and predicted gas saturation for training and testing data. Random forest clearly performs the best. It achieves an R superscript 2 of about 0.90, with low MAE and RMSE. XGBoost also performs reasonably well, but it requires much longer training time. Gradient boosting shows weaker performance and higher error. This result is important because random forest is not only accurate, it is also efficient. For practical CCUS decision-making, speed matters. If a model is accurate but too slow, it may not be useful for rapid scenario screening. So the first winner is clear. For classical machine learning, random forest gives the best balance between accuracy and speed. But numbers are not enough. Let us see the maps. Here we compare the true CO₂ saturation map, predicted map, and error map after 1 year of injection. This is important because early time prediction is critical for monitoring. If we can predict the CO₂ plume early, we can better design monitoring plans and detect unexpected behavior. Random forest produces the closest match to the true map. The error map shows only small and localized differences. XGBoost captures the general plume shape, but its error is larger. Gradient boosting shows the highest deviation. This tells us that random forest is not only producing good statistical scores, it is also preserving the spatial structure of the CO₂ plume. In reservoir engineering, a good map is more powerful than a good number because decisions are made in space. Now let us test whether random forest remains reliable over longer injection periods. This slide shows random forest predictions for CO₂ saturation at 5, 15, and 25 years. The key question is temporal robustness. Can the model still perform well as the plume evolves over decades? The answer is yes. Across these time periods, the predicted maps remain close to the true maps, and the error maps show small localized errors. This is very encouraging because long-term forecasting is one of the most difficult tasks in geological carbon storage. The reservoir is changing over time. CO₂ migrates, saturation patterns evolve, and plume geometry becomes more complex. But random forest still captures the main spatial behavior. This means the model is not just memorizing one snapshot. It is learning a time-dependent spatial pattern. Now let us look at oil saturation prediction. Now we compare the models for oil saturation prediction. Again, random forest gives the best performance. It achieves an R superscript 2 of about 0.88, with low MAE and RMSE, and it also has the shortest training time. XGBoost performs moderately well, but it is slower and less accurate. Gradient boosting again shows the weakest performance. This is important for CO₂-EOR because oil saturation tells us where recoverable oil may remain and how injection changes the reservoir. In CO₂-EOR, we care about both carbon storage and oil recovery. A model that can predict both CO₂ saturation and oil saturation is very useful for integrated decision-making. So random forest wins again, not only for CO₂ storage prediction, but also for oil recovery mapping. Transition, but can it remain reliable over 10, 20, and 30 years? This slide shows random forest predictions for oil saturation at 10, 20, and 30 years. The model consistently reproduces the major spatial patterns of oil saturation. The predicted maps are close to the true maps, and the error remains mostly localized. This is important because long-term CO₂-EOR is not only about injecting CO₂. It is about understanding how oil saturation changes over time and where remaining oil may still exist. For reservoir management, These maps can help identify areas where recovery may be improved or where injection strategies may need adjustment. The model gives us a fast underground weather map, not for rain and clouds, but for oil and CO2 inside the reservoir. Now let us ask, what features are most important for these predictions? This slide shows feature importance for the three machine learning models. Across random forest, XGBoost, and gradient boosting, the most important features are spatial coordinates, especially the z-coordinate or depth. This tells us something very meaningful. Fluid distribution in this reservoir is strongly controlled by spatial position and vertical heterogeneity. Porosity and time also contribute, but permeability components appear less influential in these models. This does not mean permeability is physically unimportant. Instead, it means that in this dataset and model setup, spatial location and depth capture much of the saturation pattern. Feature importance should be interpreted carefully. It reveals what the model used most strongly, not a universal law of reservoir physics. Still, the message is powerful. Depth is one of the main fingerprints controlling the predicted saturation distribution. Now we ask an even bigger question. Can deep learning improve the prediction further? Classical machine learning gives strong results, but reservoir saturation maps are spatial objects. They are not just independent data points. Each grid block is connected to its neighbors. CO2 migration has spatial continuity. Oil displacement has spatial structure. This is where deep learning becomes attractive. In this study, we use a 3D convolutional neural network, or 3D CNN. A 3D CNN can learn spatial patterns in 3 dimensions. Instead of treating each grid block separately, it can recognize shapes, layers, and connected structures inside the reservoir. This is similar to how image recognition models learn objects in pictures, but here, the image is a 3D underground reservoir. So now we move from predicting points to understanding volumes. Let us see how 3D CNN performs for oil saturation. This slide shows 3D CNN predictions for oil saturation after 5 years of injection. The model is evaluated on different layers, including layers 4 and 5. We compare the ground truth maps, predicted maps, and error maps. The result is strong. The 3D CNN achieves an R superscript 2 of 0.9208, ME of 0.0229, and RMSE of 0.0407. More importantly, the predicted maps visually match the true saturation maps very well. This shows that deep learning can capture the spatial structure of the reservoir more effectively than point-based classical models. Memorable line, see the map. Trust the prediction, but always check the error. First show true map, then predicted map, then reveal error map as reality check. Now let us test the most important target, CO2 saturation after 30 years. This is one of the most important slides in the video. Here, the 3D CNN predicts CO2 saturation after 30 years of injection. The model achieves excellent accuracy, with R superscript 2 equal to 0.9580, ME equal to 0.0073, and RMSE equal to 0.0117. This is better than the random forest result and shows the strength of deep learning for spatial reservoir prediction. Why is this important? Because 30-year prediction is not a short-term snapshot. It is a long-term forecasting problem. If a model can reproduce CO2 saturation after decades, it can become a valuable tool for scenario screening, monitoring design, and storage optimization. This is where deep learning becomes more than a model. It becomes a fast digital twin of the underground reservoir. Transition, now let us summarize the key lessons. Now we arrive at the conclusion. Let us step back and ask, what did we learn from this study? We started with a global challenge, storing CO2 safely and efficiently underground. Then we moved into a real carbonate reservoir with long CO₂-EOR history. We built a machine learning workflow from reservoir simulation data. And finally, we showed that both classical machine learning and deep learning can accelerate saturation map prediction. Here are the final takeaways. The first conclusion is that random forest is the best classical machine learning model in this study. It provides strong accuracy, low error, and faster training compared with XGBoost and gradient boosting. Second, random forest shows temporal robustness. It can reproduce saturation patterns over multiple injection periods with small localized errors. Third, feature importance analysis shows that depth, or the Z-coordinate, dominates the prediction, while porosity and time also contribute. Fourth, the 3D CNN achieves the highest accuracy, especially for CO2 saturation after 30 years, with our superscript 2 of 0.9580. This means deep learning can capture spatial reservoir patterns more effectively. For future work, we want to add physics-informed deep learning, including mass balance and flow constraints. We also want uncertainty maps using ensembles or Monte Carlo dropout, so the model can show not only what it predicts, but how confident it is. Finally, we will include richer inputs such as well controls, pressure, and temperature. The future of CCUS will not be built by simulation alone or AI alone. It will be built by combining physics, data, geology, and intelligent decision-making. Now let us close the video. Thank you very much for watching. If you are interested in carbon capture, underground hydrogen storage, reservoir simulation, geomechanics, and AI for geoenergy, please subscribe to this channel. My goal is to make complex subsurface energy technologies easier to understand, not only for researchers, but also for students, engineers, policymakers, and anyone interested in climate solutions. In the comments, let me know your thoughts. Do you think AI can become a reliable digital twin for underground CO2 storage? And which topic should I explain next? CO2 storage, hydrogen storage, geothermal energy, or AI-based reservoir simulation? Thank you again, and see you in the next video.